All right, we're looking at the lecture Big Booms Come from Small Atoms. The quote we have is, "And when it rains on your parade, look up rather than down. Without the rain, there would be no rainbow." What we're going to do, the learning goals for this is students will be able to distinguish between strong nuclear and weak nuclear forces. Students will be able to distinguish between nuclear fission and fusion. Two different nuclear reactions. Students will understand the mass energy equivalence principle, and students will be able to understand nuclear half-life as a tool. So we're going to look at half-life. We're going to be looking at that MC delta T, or sorry, our E equals MC squared. Looking at that. So what we already know is that protons are both positively charged, and that protons electrically repel each other, and that protons are held close together by the nucleus. So the protons are both positively charged. What we mean by that, in this atom here, we see that we have one proton here, one proton there, that they're both positively charged. And they don't like each other, but they're held together in the nucleus. What we learned in the lab is that atoms undergo fission to become more stable, and fission can be controlled using a neutron absorber. And runaway fusion, we call that a nuclear bomb. Okay, what holds the nucleus together? So if protons are positively charged and protons are all located in the nucleus, what keeps them together? What is it is a strong nuclear force overcomes the electrostatic repulsion. So what we have is we have this what we call nuclear bonding energy or nuclear binding energy, and what happens is that we have those atoms, those not atoms, but those protons that are held together by that nuclear binding energy. And so it overcomes just that electrostatic repulsion, that positive repulsion. It acts over very short distances, and so in the nucleus, everything is really combined and together, and very strong over these distances. So holding them together, that nuclear binding energy is going to hold them together. It's very, very, very strong. The what we can say about this, the reason why we have this is Yuakawa created the theories of mesons, and explained the interaction between protons and neutrons. A meson or a meson is a subatomic particle that is between the mass of an electron and a proton, and it transmits that strong interaction that binds that nucleus together. And so it binds those mesons or mesons, binds, it helps hold the nucleus together. Now, we've talked about chemical reactions before. You talked about this in chemistry. And chemical reactions are when the protons and neutrons remain constant. Protons and neutrons don't change, as the atoms connect to each other in different ways using the electrons. And the electrons that are used in chemical reactions, remember we called those, are valence electrons. And so those electrons will interact, change, switch, transfer from one to another, and we call that a chemical reaction. But when we're dealing with the nucleus, when protons and neutrons change by splitting apart or combining together, that's the nucleus reacting, so we call that a nuclear reaction. Anytime the protons and neutrons get involved and they split and they separate, that is a nuclear reaction. Now, there's two types of nuclear reactions. The first is fission. And that's when a large nuclei splits into two smaller nuclei. It's lower in energy in comparison to fusion. Fission is lower in energy. This is how we power our nuclear power plants and how we got early atomic bombs. Those are fission reactions. Still, the early nuclear bombs still had a lot of energy. We're saying that it's lower energy in comparison to fusion. Now, what fusion is, a fusion reaction is when two smaller nuclei stick together to make one large nuclei. So, two small things make one bigger thing. And that is a fusion reaction. This fusion reactions are a ton of energy. Fusion reactions are what the sun. Without fusion, we wouldn't have sun. We wouldn't have the sun. We wouldn't have sunlight. We wouldn't have life. And so fusion is a bunch of energy, a lot more than our fission reaction. Now, where does all this come from? This is probably an equation that we've seen before. We might not have thought a lot about it. E equals mc squared. It's Einstein's equation. And we see that we have c, which is the speed of light, which is 3.0 times 10 to the 8th meters per second. And we see that here. And that energy, or E is energy, which is the potential to do work. It is joules. And M is mass, is the amount of matter, usually the mass deficit or defect for nuclear reactions. And so it's how much mass we're going to use in a nuclear reaction, measured in kilograms. So let's jump into our first example. Now, in our first example, it says calculate the amount of energy stored in 1 kilogram of matter. So all we're looking at is 1 kilogram. Okay, well, we use our equation E equals mc squared. Okay, the one thing you need to think of, anytime you have 300 million squared, it's going to be a big number. So the mass is just 1, but it's 300 million squared. So 1 times 300 million squared is 9 times 10 to the 16th. And that would be joules. And that is a lot of energy. So it doesn't take a lot of mass to produce a large amount of energy. A2, it says calculate the amount of matter necessary to provide the Earth with the 6.33 times 10 to the 23rd joules of energy it uses yearly. Assume all mass is converted into energy. And so what we're going to see is that if this is the amount of energy I want, that is going to be my E. So E equals mc squared. We're solving for m, and so what we get is we get our m equals our energy all divided by c, which is our 6.33 times 10 to the 23rd all divided by 300 million squared. Okay, and we get a mass of right around 7.03, and that's a 7, times 10 to the 6th kilograms. Alright, so example A3, it says calculate the number of helium atoms that need to be fused, or they need to be fused from hydrogen per year in order to provide the estimated 300 kilowatt hours necessary to operate your iPhone 5 for 1 year. So when we're looking at this, this is going to be our energy. To go from our kilowatt hour into our unit that we need of joules, you can multiply by 3600 and multiply by 1000, and that will give us our 1.08 times 10 to the ninth joules equals our mass times our speed of light squared, 3.0 times 10 to the 8th meters per second. And that's going to give us our mass. So our mass used is 1.2 times 10 to the negative 8th kilograms. And to go from that into atoms, all we have to do is 1 kilogram is 1,000 grams. And we have that a helium has our 4.003 grams per 1 mole. And then here's some chemistry. 1 mole is 6.022 times 10 to the 23rd. We multiply all that out and we will get 1.81 times 10 to the 17th helium atoms. Now that we know that our nuclear reactions involve the nucleus, we can jump into carbon-14. Now, carbon-14 is a radioactive isotope, meaning it's constantly going to break down into smaller pieces, into more stable things. And it'll break down radioactively, meaning the nucleus will decay. Now, living organisms have the same percentage of C14 as the atmosphere. So when we exist right now, we have the same C14 as the atmosphere. And so organisms that no longer take in C14 after death. So what we can look is that we can look at the percentage of C14 in something that has died, and we can see how long it's been here. The C14 has a half-life of are 5,730 years. And so we can look at this and we can carbon date. When we talk about carbon dating, we're talking about carbon-14 dating. So a half-life graph, and what happens, and this is millions of atoms versus time. And so what we can see is that over one of our half-lives, and all a half-life is the amount of time for it to lose half of its mass. So to go from 100% down to 50%, or our 100 million atoms down to 50 million atoms, it's going to take us that 5,730 years. Going from 50% to 25%, it's going to take us 5,730 years. From that 25% down to our 12.5% is going to take us the same amount of time. And so it produces this graph that we can use to carbon date things that used to be living. Now, the half-life equation that we have, the number of radioactive molecules can be defined by where N is the number of particles of radioactive particles remaining at that time. Our N naught is going to be the starting number of radioactive particles times our 1/2 raised to our T, which is the time elapsed, and then our T sub 0.5 is the average time to reduce the number of radioactive particles by half. So this is our half-life. Let's jump into an example. When we're looking at this one, what we can say is that the half-life of a pizza has been determined to be 3.5 minutes. How long will it take to consume 87.5% of the pizza? And so when we're looking at this, what we can see is that to consume 87.5, how much do we have left? So we can think we went from 100% of our pizza, we ate 50%. We went from our 50% down to 25%, and we went from 25% to 12.5%. And so we have 12.5% left after 1, 2, 3, half-lives. And so what we can think is this multiplied by 3 different times, which would give us 10.5 minutes. Okay. Jumping down into example B2, it says how long will it take to reach 25 million atoms of C14? So if we start at 100 and we go 1 half-life is down, that's 1, that's down to 50 million, and then one more half-life, which is 2, will get us to 25 million. So that is 2 half-lives. So the half-life of C14 is 5,730 times our 2 half-lives will give us right around 11,460 years. And our jumping into our last example, it says potassium 40 has a half-life of 1.27 billion years. A scientist suggests using potassium 40 to analyze the earliest human remains believed to be 100,000 years old. Confirm or dispute this suggestion using the clear method. So what we would say is that if we're going to look at our early remains believed to be 100,000 years old, well, the half-life of potassium 40 is 1.277 billion years. And so what we would see is that we wouldn't even have any particles decaying since 100,000 years. And so we wouldn't even have one half-life to be observed, and so therefore we could not use our potassium 40 to look or confirm any human life 100,000 years ago.